Organic compounds. We're just going to learn a teeny tiny bit about organic compounds. Chemists use the word organic in a very different way than activists or health-conscious people or grocers do. Organic means that the compound is most likely from some sort of a living organism. It does not mean that it's safe or good for you. Okay? Many organic compounds are deadly toxins. Originally, the division was made, things that were from living organisms were called organic, things from non-living organisms were inorganic. And it was observed that organic compounds could be decomposed much more easily than ionic compounds. Many of them are combustible, they'll burn. But it was easier to make the inorganic compounds in the lab. Now, of course, we can make pretty much anything in the lab. So something is considered an organic compound if it's composed of carbon and hydrogen. It has to have carbon and hydrogen. If it doesn't, it's not an organic compound. It can also have some other elements in it like oxygen, nitrogen, phosphorus, sulfur, or there's other trace elements that might be in there. But the key thing is carbon. And here's the structural formula and space-filling formula for methane. Methane is an organic compound. Carbon and 4 hydrogens. Carbon has a very unique chemistry, and you may have heard if you are into science fiction, they talk about carbon-based life forms, right? We are a carbon-based life form. The structures of the molecules in our body contain a lot of carbon, and carbon is unique in that it forms bonds with other carbon atoms and can make long chains of atoms, so you can get very long molecules. It can also make rings and different branched structures. And other elements don't do that very much. Silicon does a little bit, and if you look at silicon, it's in the same family as carbon, right? And so some people, are intrigued by the idea of there possibly being a silicon-based life form. I don't know. Carbon always forms 4 covalent bonds. They can be single, double, or triple bonds. And they can be with other carbon atoms or with different elements. Here's some examples. Here we see, this is called a ring structure. So the carbon atoms, it looks like they're playing ring around the rosy. Here they're in a straight chain. This is a branched chain. Here we have a double bond, a triple bond, and here we have carbon bonding to oxygen as well as to another carbon atom. Hydrocarbons are organic compounds containing hydrogen and carbon, as the name suggests, hydrocarbon, hydrogen, carbon. So we've got all compounds, we've got inorganic and organic, the division. And then organic compounds are divided into hydrocarbons and functionalized hydrocarbons. Hydrocarbons make very good fuels. They burn well and they burn cleanly. They form CO2 and water, neither of which is particularly harmful. So things like oil, gasoline, liquid propane, natural gas, these are very common hydrocarbons. The reason that burning these sorts of fuels can increase pollution is not because of the hydrocarbon itself, it's because of the other stuff in the gasoline. And could we purify it? We could, but it's not cost effective. So there's trade-offs there.
So we'll just die young.
Well, I'll just die young, yeah. But we'll be happy, as opposed to being, cold and only eating raw food, hunting for things.
I like sushi.
Sushi's good. So there's a very specific set of naming rules for organic compounds. We're going to just scratch the surface. So organic compounds have a different set of rules. Hydrocarbons where there are all single bonds are called alkanes. And we change the ending to -ene, alkene, if there are double bonds present. And it gets changed to alkyne if there are triple bonds. The base part of the name is determined not by carbon, but by how many carbon atoms are present in the molecule. And then the suffix tells us whether there are multiple bonds. So the prefixes are the same except for the first four. Instead of mono, di, tri, and tetra, we use meth, eth, prop, and bute. I have no good explanation for that, but it's what we do. So we do need to remember that. The way I remember that is a mnemonic: Mom eats pickled bananas. 1, 2, 3, 4. I'm not sure you can actually pickle bananas. I know I don't have much time, but I'm curious. Can you pickle bananas? Not pick
Checking
up.
my sources.
No.
Oh,
Can you pickle bananas?
let's see. Okay, I found this on the web for can you pickle bananas.
It's just a bogus website. Okay, that wasn't so fun. Anyway, it makes me think that Mom might be pregnant if she's eating pickled bananas. Anyway, methyl, ethyl, propyl, butyl for 1, 2, 3, 4. Pardon me? They pickle green bananas. Good to know. Thank you. So methane, that prefix meth means one carbon. So here the formula has 1 carbon in it. It doesn't specify how many hydrogens because we can figure it out. There's 1 carbon. The carbon has to have 4 bonds. So you put hydrogens around it so it's got 4 bonds. Propane, the prefix prop means 3. 3 carbons, and then you fill in the required number of bonds with hydrogens. This is what we use LP gas in the outdoor grill. Butane has 4 carbons. Pentane has 5 carbons. You get the idea. Ethene, eth means 2. This has 2 carbons. Ethene has a double bond. So these 2 carbons have a double bond, and so that's two bonds for this carbon, and then it's only got 2 hydrogens. So ethane would be 2 carbons, but only a single bond, and so ethane would have more hydrogens because we put those hydrogens around so we get 4 bonds on all the carbons. Ethyne has a triple bond. Any questions? So there were hydrocarbons, and then there are the functionalized hydrocarbons. The functionalized hydrocarbons have what's called a functional group. They have something unique, something different, that adds a different sort of function to the molecule. This is going to affect its physical properties and its chemical properties, the types of reactions it undergoes. So there we talk about families of alcohol. Alcohols are a family of functionalized hydrocarbons. So methanol, isopropanol. So we see these prefixes in here. Methanol, that is a little bit like the word methane, which is CH4. But this ending "ol" tells me it's an alcohol, and so we put this OH in here instead of one of the hydrogens. I'm not gonna require you to name or draw structures for functionalized hydrocarbons, just the regular plain ones. But each of these has an OH functional group on it. So here are the different functional groups: alcohols, ethers. You might come across a question in a homework or a worksheet or something where you have to identify what family this organic compound is in, and I would expect you to go look at this table and try to see which of these it matches up with in terms of a pattern. So aldehydes, ketones, carboxylic acids, esters, and then amines have nitrogen in them. So one of the carbons been swapped out for a nitrogen. And here are some of the places you might encounter these types of compounds. So let's draw the structural formula for nonane. How many carbons would this have? 9. Okay, so this is the sort of math that you have to deal with in organic chemistry. 3, 4, 5, 6, 7, 8, 9. It's a lot of counting, and usually not past 10 or so. So there's my carbons. How do I know how many hydrogens to put on there? I need each of these carbons to have 4 bonds.
It's only single bonds, right?
Yeah, the ane tells me it's only single bonds. If it was nonene, it would have at least 1 double bond. And the really correct name of it would have to specify where that is. But we're not going to go that far. So, because carbon always has 4 bonds. It has to do with the octet rule. We will learn perhaps more than you want to know about the answer to that later. For now, just carbon always makes things with 4 bonds. It's very nice and predictable that way. Okay, so that's the structural formula for nonane. If you needed the empirical formula, then you would count them up. It would be C9, and if you count up all those hydrogens, there's 20 of them. This is sort of a condensed structural formula because writing all these H's gets really tedious. So what this means is these 3 hydrogens are attached to this carbon. So there would be 3 hydrogens off of that one. There's 2 off of this one and 3 off of that one. So you could draw it like this. It's just tedious. What family does this one belong to? Well, let's look at the special part. So this oxygen is different than just carbon and hydrogens. And here we have an oxygen double bonded to the carbon. We also need to look at what else is bonded to the carbon. We have a carbon on this side and a carbon on that side. So we go back and look at the chart. We're looking for, oh, there's one, double bond between oxygen and carbon. R here stands for a hydrocarbon, just carbons and hydrogens. In this one, we've got a hydrocarbon on one side and an H on the other side. So this is one example. We've got carbon on one side, but only hydrogen. So that's not the right one. Here we've got carbon with a double bond to oxygen, and this one has a carbon on each side, and so that's the correct family. That one's a ketone. Any questions?